All right, so what I'm going to be doing in this mini lecture is I'm going to be talking about the intermediate value theorem. And in specifically, how do we use, say, for example, a proof like this or information like this in order to prove something? Okay, so the intermediate value theorem depends upon our definition of continuity. Okay, and then there is some logic that goes along with it that oftentimes is not explained to students. So I'm going to go out and explain it. So first, just remember that a function f of x is continuous at a number a if the limit as x approaches a of f of x equals f of a. Okay? And now the intermediate value theorem is going to tell us that suppose that f is continuous on a closed interval. Okay? Now closed interval meaning including, right, includes a and b. Yes? So it's going to include a and b, and let n be any number between f of a and f of b, where f of a does not equal f of b. Okay, so basically we need these two things, these two values, right, to not equal each other. That's going to end up being really important. Then, okay, there exists a c belonging to a to b such that f of c equals n. Okay, so basically what this is saying, if we think about it, or well, if you read it and you spend some time really reading it, is n is a number between f of a and f of b. So n is on the y-axis, right? So this is a y value, or a value for the function, okay? And c is an x value. So essentially what it's saying is it's saying if n is between f of a and f of b, like it's somewhere in the middle of those two, okay, f of a and f of b, all right, and the function is continuous, so f is continuous on the closed interval, right, then we know, right, it's essentially kind of like there's no breaks in there, so consequently we know that there's got to be some c on the x-axis that's going to give us, all right, the value of n. It'll make f of c equal to n. Okay, so our n is a y value between f of a and f of b. Okay, and our c value is somewhere in between those two. Okay, is somewhere in between a and b. Okay, so let me draw a picture of this to kind of help us think about it. Okay, so let's imagine, okay, that I've got here's a and here's b. They're on my x-axis. Okay, and here is f of a. All right, so there's f of a, and here's f of b. So notice f of a does not equal f of b. Okay, that's good, right? We need that to be the case. And then also we see that f is continuous on the closed interval. So basically, if I imagine what this looks like, it might look like something like this. Okay, there is my function. It doesn't have to look like that, but it does have to be continuous on this closed interval, right? Meaning that we also have values for a and b. Now, I'm going to pick an n. Here's n, okay, right? And what I see right now, okay, is that if I take n, it's on my, and I go out to the function, all right, I see that the function does hit at n. In fact, it has to, right? Because it's continuous. There's no breaks here. The only way it couldn't hit n, right, because n is somewhere in those y values, is if we have like a jump or if we have some kind of discontinuity, right? But we don't because it's continuous everywhere on that interval, all right? So there's that n, and so what the theorem is saying is that here's c, okay? So f of c equals n. That's all the theorem is saying. It's basically saying, okay, if I imagine that I've got a continuous function, all right, okay, and essentially what I'm trying to do is I'm going to say, all right, well, on this, right, I've got a to b, my x values, okay, and they've got an associated f of a to f of b, which are the y values. If I pick anything inside of those y values, any value in those y values, okay, then f of c is going to equal n. There's going to be some c that'll do that. Okay, there will be some c that'll do that. So let's take a look at how this actually gets used. So how we use something like this, or how we use the intermediate value theorem, is we're going to get questions like this. Use the intermediate value theorem to prove that the square root of x minus 4 equals negative x cubed. Okay, and it has a solution on 0 to 5. You're like, well, okay, what do I do? Well, the thing is that if you notice here, this one's actually kind of difficult to go out and actually go through and solve, right? algebraic systems will be able to, but it's a pain in the butt, right? And besides, they didn't ask us for what the solution was. What they asked us for was to show that it has a solution. We want to prove it using the intermediate value theorem. So we're going to use that theorem. Make sure you go take a look back at it to see what it says. So first, okay, 0 to 5 is a closed interval. Okay. In addition to that, all right, and you'll have to think about how to do this, the square root of x minus 4, okay, the square root of x, negative 4, and negative x cubed are all continuous on 0 to 5. And the reason why we know that is because the square root of x is a radical function, okay, or a root function. And so it's defined everywhere where it's greater than or equal to 0. So x has to be greater than or equal to 0. Great. Negative 4 is a constant. It's defined everywhere. And negative x cubed is a polynomial, so it's also going to be defined everywhere. So, right, what we get here is we're going to define this function f of x equal to square root of x minus 4 plus x cubed is continuous. Okay? So what I've done is I basically just turned this whole thing, I've turned that whole thing into a function, right? By moving over the x cubed, okay? By moving over the x cubed. Now, I want you to notice something, all right? I did this, right, because the solution did this. The solution to the square root of x minus 4 equal to negative x cubed is the square root of x minus 4 plus x cubed equal to 0. Okay? So I need to prove that, in fact, this function here actually equals 0 somewhere on the interval. Okay? So I need to prove that f of x equal to the square root of x minus 4 plus x cubed equals 0 somewhere on 0 to 5. Okay? And let me just go back for the second, go back to the definition. You're going to see why. Suppose that f is continuous on a closed interval, a to b, and then we say let n be any number between f of a and f of b. Well, we want to see, does 0 exist? So in this case, our n is going to end up equaling 0. Okay? Then, if that's the case, right, okay, then there exists a c from a to b such that f of c equals n. So if I have all of this stuff true right in here, okay, all of that true, then what I get is I get this part true, which is what I'm trying to prove. Okay, so let's go back to our problem. So now I have this function f, okay? F is continuous on a to b. Or 0 to 5, excuse me. The next part that I need to prove is I need to prove that 0 is actually between f of a and f of b, right? Okay, right? Want to show 0. So I need to show that 0 is between f of 0 and f of 5. Okay? All right? So that's my interval. F of 0 to 5, that's my interval. So all I've got to do then is just plug in 0. So f of 0 is going to equal square root of 0 minus 4 plus 0 squared, 0 cubed, excuse me, which equals negative 4. And f of 5 is going to equal the square root of 5 minus 4 plus 125, right? Which is greater than 0. So it's positive, right? It's positive. Strictly greater than 0. I don't even need to know what it is. All right? So 0 f of 0 and f of 5. Think about that for a second. F of 0 is negative, f of 5 is positive, right? So 0's got to be somewhere in there, all right? So that's the second part, or the third part, actually. The second part. First, right, we showed that f was continuous on 0 to 5. Second, we showed that 0 was between f of 0 and f of 5. So by the intermediate value theorem, IVT, by the intermediate value theorem, okay, there exists a C on 0 to 5 such that f of c equals 0, right? So we don't actually need to go out and solve it. All we're doing is we're showing that it exists, that the solution exists. How did we show that the solution exists, right? By, in fact, going in, using the intermediate value theorem, right? Showing that f was continuous, showing that 0 was between f of 0 and f of 5, and then just stating, by that theorem, we get f of c equal to 0, okay? We're going to do a couple more problems. I'm going to do one more problem here, and then we'll do another problem or two or maybe even three in class. All right. So let's say, for example, I want to do this. Show, using the IVT, that e to the x equal to the square root, or equal to 20 minus the square root of x, okay, is solvable, right? That we actually do have a solution for this. Okay, so e to the x equal to 20 minus the square root of x is in fact solvable. Okay, all right. So first what I want to do is I want to generate a function. So we're going to say f of x equals e to the x minus 20 plus the square root of x, and that's our function. Okay, so it's a function. Where, the second part, is where is f continuous? Right? If we look, e to the x is an exponential function. It's continuous everywhere. 20, constant function, also continuous everywhere. Square root of x, radical function, okay? And so consequently, we'll have to have it, it's only defined when x is greater than or equal to 0, okay? So f is continuous if x is greater than or equal to 0, okay? Great, totally got it, right? Now, 3, okay, I am trying to determine if f of x equals 0 anywhere. So what I'm going to need to do is I'm going to need to define some x's. So I need to define an x interval. After a little bit of playing around, okay, what we get is that f of 0 is going to equal e to the... On the other hand, if I pick out another number, say for example I've got f of 3, on the other hand, if I've got f of 3 is going to be e to the third minus 20 plus the square root of 3, okay? This ends up equaling 1.8175, okay? Awesome. So 0 is in, okay, or we also say, we use the phrase is in f of 0 to f of 3, okay? Or what we also write is 0 belongs to f of 0 to f of 3. Hence, f of c equals 0 for some c in, okay, c belonging to 0 to 3. Okay? By the intermediate value theorem, by the IVT. So, e to the x equal to 20x is solvable. Okay? So what we did first was we generated a function from our equation here, okay? Just by basically moving everything over to one side. And then we figured out where f was continuous, right? On what interval, okay? And then utilizing our rules of continuity, and then I basically had to generate an interval. I generated an interval where 0 was in that interval, okay? Since I could find that interval, right, by the intermediate value theorem, right, there must be some c where f of c equals 0, right? And that then gave me something that was solvable, okay? So these two examples are meant to kind of like show you how it is that we use the intermediate value theorem to do some proving. Some key things to get about this, some key things to remember is that frequently with the intermediate value theorem, we're not actually looking for what C is. We don't care, okay? All we want to know is that it exists. And so we fulfill the pieces of the intermediate value theorem, and then that gives us the fact that C does in fact exist, okay? So this completes the mini lecture.